Hello, welcome to today's Nakanon webinar. This is a second webinar in the series of resilience to geohazards. My name is Sharon. I'm calling in from Montreal in Canada. This is an international webinar with the presenters in WSP in New Zealand. I will just mention briefly the housekeeping items before we get going. The presentation slides are available to download in the handout box as a PDF. And also there will be time for question and answers. The webinar will be around 45 minutes long, around 30 minutes presentation and 10 to 15 minutes of Q&A. We welcome you to ask questions in the question box on the control panel. So I'll hand it over to Brava and Doug to start the presentation. Thank you.
Thanks, Sharon. Well, welcome everyone. So today we're going to talk about some of the research that we've been carrying out following the Kaikoura earthquake, and particularly relating to the design of earthquakes and slopes. So just a little bit about ourselves before we get going. So my name's Doug. I'm an engineering geologist with WSP in Wellington in New Zealand. Been with the company a wee while now, coming up 20 years. Started off with engineering geology for infrastructure projects, but more recently, over the last sort of 10 or so years, been more focused on natural hazards and the impacts of landslides and other hazards on infrastructure.
And myself, I'm Prabha Haran, and I'm a National Technical Director based in Wellington, same place as Doug, and I specialize in geotechnical earthquake engineering and resilience. A fun fact, I just use one name, Prabha Haran, because in the Tamil ethnicity, we just use one name. So I've been focusing on resilience for the last 25 years, and about 15 years ago, we decided to establish a focused risk and resilience team within WSP in Wellington. And this is a specialist team which focuses on how we can improve the resilience of our communities, our infrastructure, and our built environment, and includes a range of geotechnical engineers, geologists, seismologists, and GIS hazard analysts. Back to you, Doug.
Yep, okay, so just a brief outline of what we're going to cover today. It's important to set the context for the research and what the gaps and the current issues are in our practice, and then we'll outline the research that we've done, and really the main topic will be how the slopes in Kaikoura performed, and then what the lessons are for resilience-based design for slopes for future. And then we'll just finish up with some key highlights and then Q&A at the end. So to begin with, just to set the scene somewhat, for those of you who may not be from New Zealand, we have a peak boundary running right the way through the middle of the country, which understandably causes us a few issues to deal with for our infrastructure. So because this is an active plate boundary zone, we've got high seismicity, and with the compression from the tectonic plates, we've got lots of uplift and erosion, and therefore rugged terrain. So all of our infrastructure, including transportation routes, towns and cities, are often formed on or near these slopes. And so the performance of these slopes in earthquakes, as well as other hazard events, is really critical for the resilience of our communities and our built environment. So this is the Kaikoura area at the top of the South Island, right where the Pacific Australia subduction zone comes onshore and transfers into strike slip faults. So it's a very busy area, tectonically speaking, and this is what we're going to focus on for today. So as you can imagine, with all of this active seismicity, we do get a lot of landslides and slope failures triggered by earthquakes in New Zealand, and as you can expect, these have caused a lot of damage, including loss of life and damage to infrastructure. But despite the demonstrated hazards posed by landslides and earthquakes, there are still some gaps in design practices for geotechnical features such as cut and fill slopes, and so that's really the focus for us today.
So let's have a look at what our current and recent practice looks like. We have major infrastructure projects, not just in New Zealand and around the world, and often they require large earthworks, high cut slopes, and often near steep slopes. And that is definitely true here in New Zealand with the rugged terrain Doug talked about. So, but design has typically involved traditional slope stability analysis, which was developed primarily in stable continental environments like Europe. And then they have been modified and extended to do pseudostatic analysis, which we'll talk about later. Or design has been based on precedent. Precedence is looking at how things have performed in the past. But we haven't had many events in the past 75 years until the last 10, 15 years. So as a result of that, there has been limited guidance or standards in New Zealand. And when we started this research, we looked at internationally, and even internationally, there is very little guidance for design of slopes for earthquakes. So we kind of set out to see how we can understand this better. In particular, there was limited understanding of the slope failure mechanisms in earthquakes because they're not always the same as what you get in other trigger events like rainfall. And therefore, this has led to a lack in the seismic design of slopes, leading to poor resilience, or sometimes unnecessary costs because people were not recognizing the mechanisms and the resilience issues. So let's go to the next slide. So the gaps we saw which needed to be filled for improving our earthquake practice is that we needed to understand the resilience of existing infrastructure in earthquakes so that we can make sure that we can improve them so that we can ensure our communities can survive and thrive. The second thing is we needed to understand the slope failure mechanisms, as I mentioned, and therefore we could take that into account in the design. We need good guidance on design, which is underpinned by the resilience context in which we are designing these facilities. And we also need to improve the recovery and associated outage times because when you have a large earthquake, inevitably you'll have some failures. So we need to understand how we can quickly recover from that and also design so that we can recover quickly. And finally, we need to improve the uptake of research into earthquake design practices. Can go to the next slide.
So some of the specific gaps, I guess, about that last point of improving the gap between research and practice. A lot of earthquake-induced landslide research has focused on sort of area-wide or regional-wide processes and factors. So looking at geographical distribution of landslides and the contributing factors, there's some examples on the right of the typical types of factors that get analysed, and using these as proxies, I guess, for the processes that actually contribute to landslides. And so these are very useful for looking at landsliding on a regional scale. So for susceptibility assessments and even for forecasting for future events, but they're not detailed enough to be used for engineering design at a local scale or a site-specific scale. And so some of the things that we need to draw in from research, like Barbara mentioned, what the specific mechanisms of failure are that are important for earthquake-induced landsliding, how the ground shaking gets modified by the slopes, and in particular by the modification of the slopes. So when you're cutting into a slope, how does that modify the response of the slope to ground shaking? And then what are the impacts of failures once they've occurred? So landslide run out and inundation of infrastructure by debris, and then what the sort of follow-on impacts are in terms of recovery and outage times. And so all of these are critical to understand resilience kind of holistically. So not just what happens to a slope when it gets shaken, but then what happens afterwards in terms of recovery and impacts, so that we can enable our designs to better improve the resilience of our infrastructure. And just to put this in a bit more context now, this is a piece of work that we did in the year leading up to the Kaikoura earthquake, so very conveniently timed, looking at the national state highway network and its vulnerability to high impact, low frequency natural hazards. So this map shows the areas of potential blockage to the state highway network in the South Island from a large magnitude earthquake. So it's not any particular earthquake scenario, just a general large degree of ground shaking. And so it shows that across the state highway network, you've got areas of significant vulnerability to damage from large landslides, liquefaction and lateral spreading, and collapse of slopes and retaining walls. And so on a network level, you can see what the consequences are of any one of these links being taken out by an earthquake. And it just highlights the importance of slope failures in this particular part of the country for the resilience of the network, and also what the consequences are for the wider availability. So if one section gets down, there aren't many detour routes available, and those go through fairly hazard-prone terrain themselves. And then all this was thrown into sharp relief when the Kaikoura earthquake happened. So this earthquake occurred at 2 minutes past midnight on the 14th of November, 2016. And it was a very big, large magnitude earthquake, 7.8, which involved a large number of faults over a wide area. So it's a very complex event seismologically. And correspondingly, there was strong ground shaking over this entire area, so over this whole 200-kilometer odd distance. And this is a relatively sparsely populated part of the country, fortunately. So it's very mountainous in this area. And so it triggered a lot of landslides. That was the principal ground damage caused by the earthquake. There were only 2 fatalities, thankfully. And then the major impact of the earthquake was that all of the infrastructure networks that were running along the coast through this area were severed by landslides. Principally the road and the railway corridor, which run, you can just see them out here, run along the coast. And there was then a major rebuild starting straight after the earthquake and for about 5 years. And so really this earthquake gives us the opportunity to document how engineered and unengineered slopes performed in earthquakes, and also what the impacts of those slope failures are. So it gives us a real good natural laboratory to investigate these sort of aspects.
Actually, we started off looking into this after the Christchurch earthquake of 2010 and 11. The New Zealand Transport Agency asked us what issues we need to be considering and engaged us to do some research to provide some guidance for the seismic design of slopes. So we developed this guidance you can see on the right-hand side, which was published in 2018. And before that was finished, came the Kaikoura earthquake, as Doug mentioned. So on the next slide, we were approached by the Ministry of Business Innovation, Employment, and Crown Research Institute, GNS Science, to be part of a $9 million research program over 5 years to look at how landscapes respond to earthquakes. So there were 7 themes, and we led one of the key themes, which was the practical aspects, looking at performance of earthworks and the resilience of the built environment. The other teams were led by the Crown Research Institute and a number of universities. There was also an international science advisory panel to kind of engage so that we can learn from and also disseminate the learnings internationally. Next slide, please. So our engagement covered, we set out to do 5 things as part of this research. One is map the landslides and understand the failure mechanisms and how they impacted on the resilience performance of infrastructure. And then we selected and investigate some of the sites representative of different types of failures in a bit more detail. And then we analyzed them to draw insights from these failures. And then considering all the mapped landslides as well as the insights from this detailed analysis, we developed some guidelines for the design of earthworks. And then we set out to disseminate the learnings and guidance. This Global Snack and Learn webinar is part of that dissemination process. Go to the next slide. So the aims of the research was to develop recommendations for resilience-based design of slopes and associated assets, how we can manage landslides, and also enhance the resilience of New Zealand's infrastructure through a better knowledge of how cut, fill, and adjacent natural slopes perform in earthquakes, and how we can recover from major hazard events. Hand over to you again, Doug.
Okay, thanks. So now let's get into a bit more detail of what actually happened in the Kaikoura earthquake. So as I mentioned before, there were over 30,000 landslides triggered by the earthquake. And so these are these blue dots you can see highlighted here. And so these caused the principal damage to the infrastructure. So landslides and rockfalls, debris flows as well, particularly after the earthquake, as well as slumping and failure of embankments and retaining walls and damage to bridges and tunnels. So all of these damage impacts closed the road and rail over this entire stretch. So the colored dots you can see there, the blockage or the damage sites. The color indicates the severity, so red being closed and yellow being sort of partly closed. And because this was the main arterial route between Christchurch and Picton up the east coast, the only available detour route was through the Lewis Pass over this way through the Southern Alps and then right round. So this added about 140 kilometers to what is normally a sort of 3.5, 4 hour car trip. And so particularly for the trucks, which were then taking a lot more freight because the railway had been taken out of service, this added a lot of indirect economic impacts. And then on top of that, of course, was the rebuild, which ended up being about $1.3 billion, which was fairly significant for a country of New Zealand size. And so mentioned before that we'd done this resilience study for the state highways leading up to the earthquake, but we'd also looked at this in a bit more detail about 20 years earlier as part of a pilot study looking at the effects of earthquakes on roading networks. And this was really useful just to compare what the expected vulnerabilities are with the actual. So like the study done in 2016, it was not for any particular earthquake and certainly not for something as complicated as the Kaikoura earthquake, but it's useful just to compare what the damage effects were anticipated versus reality. And so you can see that overall the locations of damage compare fairly well, which is good to know because this is not a prediction as such, but it shows that these sorts of hazards can be anticipated. So we can use this information and these observations to look at other areas of the country and for planning for future earthquakes. And so slope failures were the main form of ground damage that caused this prolonged closure of the state highway and the railway through Kaikoura. And so the types of slope failures and their impacts were influenced both by the topography, but also the form of the road or the rail. So the large landslides from high hill slopes were the ones that caused the biggest impacts. So these resulted in large volumes of debris, which understandably took the longest to clear. Slumps and rockfalls from lower slopes, and particularly cut slopes, caused less disruption, but tended to then require longer mitigation and stabilization work. And then embankments were widely damaged, and while these didn't necessarily close access, you could still get four-wheel drive access across some of these types of failures with cracking. These repairs tend to take a lot longer for excavation and rebuilding the embankments. So just look at some of these different types in a little bit more detail. Cut slopes were all over the study area were affected, and so there's a variety of geology and different types of heights and angles of slopes. And the common modes of failure were shallow rock and debris slides, and these generally cause little disruption. So the examples you can see on the left-hand side there either didn't reach the road, or if they did, were fairly easily swept up quickly. The deeper seated, more structurally controlled failures in rock cause more damage, both from the larger volumes of debris, but then more impact from the need to construct slope stabilization measures or rockfall protection structures afterwards, before access could be completely reopened. And like I mentioned, failure of natural hill slopes caused the most damage and disruption, and these tended to be dominated by rock slides and debris avalanches. And these also had a range of volumes and impacts, from negligible, so where debris didn't reach the transport corridor, through to really long duration closure. So the state highway through this, through Kaikoura, was closed for 13 months, and that was due to one of these debris avalanche, rock avalanche failures, which took a long time to clear access. And so this long outage was due to the need for scaling and sluicing to make the site safe before the earth-moving plant could get in to start clearing the debris to restore access. So there was extensive damage to embankments over about a 200 kilometre length of the study area, and the predominant modes of failure were consolidation, settlement, slumping of the edges of the fill slopes, and then displacement of the embankment, as well as the underlying natural soils. A lot of these were constructed in the late 1800s, and they were built by hand by cutting from one side of the road and tipping it onto the downhill side to form the bench. And so damage was particularly severe in the Hunderley Hills, which is in this area here, these two, where the road crossed pre-existing landslide features or infilled gullies. And settlement of fills at bridge abutments was also common, and this prevented access even if the bridge was actually undamaged. And there wasn't much liquefaction in the earthquake, unlike, say, Christchurch, but there were a few places around Kaikoura and Blenheim and low-lying areas where embankments were damaged by liquefaction or spreading. And I'll just touch quickly on retaining walls. There wasn't a focus of this research as such, because there is some guidance for earthquake design of retaining walls, but it's still useful because these were often constructed alongside or within embankments, and so the performance of these and the performance of embankments was important for overall access. And as you might expect, recently engineered and constructed and particularly anchored retaining walls performed well, and gravity walls that were unengineered and unreinforced performed poorly. And so the dominant types of failures were from overturning, and there's a couple of examples shown there, as well as some translation as well. And often these were built, for example, this type of situation, single height gabion walls were built to improve the safety of the corridor, to allow guardrails to be constructed. But then in the earthquake, they caused more damage than if they hadn't necessarily been there, because they sort of tended to drag the road surface with them, and so caused more extensive cracking and damage than otherwise. And so, as Barbara mentioned, our scope for this research was to map the failures that occurred and investigate some key ones and analyze those to understand what the key factors are that drove the performance. And so some of the important issues that we've identified that we need to consider in a local or a site-specific assessment are highlighted here. So firstly, what are the appropriate seismicity parameters to use in an assessment, and how do we account for amplification of the ground shaking? The second is to understand what the material properties of the slope are and how those will behave in response to deformation during the earthquake. And then thirdly, what are the realistic or appropriate failure mechanisms to use? And so those three really cover the initiation of failures. And so what we might typically do for a design of a cut slope, for example. But observation from Kaikoura also shows that it's not just the failure initiation that we need to be worried about, it's the consequences afterwards. And so those aren't necessarily well covered in design approaches. So we need to understand what the mechanisms of transport and run out of landslides are, and these will differ depending on the failure mechanism. We also need to consider what the post-earthquake damage state of the slope is likely to be and what sort of hazards might exist after the earthquake. And then finally, what the effects of slope failure are on resilience of the wider networks and not just the local site-specific impacts, and also for recovery. And so some of the high-level sort of key observations from that, just explore those in a bit more detail now. Failure mechanisms, just highlight a couple of the key ones. Rock mass failures were widespread in the Greywacke Hills, which is, for those of you who might be from overseas, it's a common basement bedrock across New Zealand, and it's very highly fractured, very intensely fractured, and can be completely weathered in the upper parts of slopes. And so many shallow failures occurred on these materials in these situations. Tend to be shallow seated in the near surface zone of weathered rock, as well as in weaker, more younger rock materials. And so importantly, these tended to show quite brittle behavior. So they initiate as sliding and tensile release along these very closely spaced interconnecting joints. And then as the displacement continues, they lose strength and collapse and become debris and rock avalanches as the failure mass disaggregates. And so, like I said earlier, these were the types of failures that caused the most significant disruption and damage to the transport corridor. And so, just as a sort of a note for what Brad will come to in a little while, because these occur on natural slopes, so unmodified, they're not necessarily something that we may deal with in design as such, but we need to think of ways to mitigate the effects if they occur. So it's part of an assessment approach that we need to consider, even if we're not going to be cutting into or building on top of these slopes themselves. And the structural geology plays a very important part on the mechanism of failure as well. Some important examples here are the en echelon stepped path failures, which consist of sliding on these unfavorable outward dipping joints, which are separated by failure across shorter persistence, more steeply dipping steps. Then there's a combination of sliding on these persistent planar defects and shear failure, either through a secondary defect or through shearing through weak rock mass at the base of the slope, as well as planar sliding on persistent discontinuities such as bedding, or in this case, a fault plane. And these types of failures are also showed brittle behavior, with large runout causing extensive impacts. And so this really underlined the need to understand and characterize the structural geology of a slope so that these failures can be assessed and appropriately. On the other side of the coin, the engineered fill materials showed more ductile behavior, unlike the rock slopes, and that they tolerated displacement without significantly losing strength. And so none of the fill slopes in Kaikoura disintegrated into flow or avalanche type failures. So for example, the embankment shown here on the right, there was excessive displacement due to high groundwater, but even then the failure mass didn't completely disintegrate. And incidentally, the high groundwater was a factor of, you can see here this line, this is a culvert. So there was a farm pond constructed on the uphill side, but this culvert was completely blocked when this was uncovered, which highlights the need for good proactive maintenance of things like drainage. And so the common failure mechanisms of fill slopes in Kaikoura were settlement and displacement of the slope crests and slumping of the fill and underlying soils. And so this manifested as generally as cracking and displacement of the road surface and slumping of the railway ballast. The cracking along the roads tended to be quite quick to reinstate for emergency vehicles, either by using temporary fill or by just excavating and releveling the surface. And so this shows that a sort of standard approach of designing embankments to allow for displacement is appropriate, provided, of course, that this is backed up with good quality construction, supervision, and regular maintenance of things like culverts and drainage. And then looking at the impacts of slope failures, landslide runout was the main cause of damage in Kaikoura. So principally inundation by debris, so burying of the transport corridor and damage of things like retaining walls and guardrails. So different types of landslides result in different runout extents. Debris avalanches and particularly confined debris flows will go much further than things like slumps and more deeper seated slides. And then the volume as well plays an important part. So the larger the volume, the further the reach will be. But it's not just the landslide that reaches, it's not just the debris that reaches the base of the slope where your infrastructure happens to be that causes the problem. The outage time in Kaikoura from the landslides was heavily influenced by these areas of perched debris on the high hill slopes and areas of damage. So in this example here, a lot of time was spent scaling and sluicing these upper parts of the slopes because there was a lot of debris and large boulders sitting up there that were causing potential safety risks to the people that needed to get in at the toe of the slope to clear the debris. So these are all important considerations. And it's important also to keep in mind that the hazards from slope failures don't go away just once the ground stops shaking. In Kaikoura, only a small proportion of the slopes actually failed in the earthquake, but there was deformation of slopes and cracking, and then there were significant failures after the earthquake due to rainfall. And so these included, the types of failures included new landslides like this one shown here, as well as debris flows from existing debris that was perched higher up the slopes. So now hand back to you, Bravo.
Okay, thank you, Doug. So I'm going to give a brief overview of some of the resilience principles for design we have developed. So the ability to quickly recover and resume original service is a key aspect of resilience. So being able to recover functionality is the key aspect. And so we have developed this diagram, which Doug's going to show. So we have a normal level of service, and then comes an event, and that leads to a reduction in the level of service or functionality. And then it takes some time to recover functionality back to original level. Sometimes we can do better, or sometimes we have to accept a lower level of functionality because of the damage. So this triangle, this pink triangle indicates kind of resilience. The smaller the pink triangle, the greater the resilience. So that could be by a combination of reducing the loss of functionality or being able to recover quickly. But in reality, we don't get a linear recovery. So often we can recover some functionality, and then it takes more time to recover functionality in stages as we carry out the work. You can go to the next slide. So in terms of design, we used to do just life safety design. The focus of earthquake design was on life safety because a lot of people died. And then we moved on to consider displacement. So we were able to do displacement place design, like Doug mentioned, for embankments. And then later on, it kind of evolved to look at performance because displacement itself doesn't mean much. So how does it affect performance? And then through this research, we are proposing a more resilience-based design. So it's not just performance, but functionality and ability to recover quickly, which matters. So the next slide. So early focus on resilience is crucial to be able to achieve good resilience. To do that, we need to understand the resilience context. As Doug showed and see on the right-hand side, we need to understand the if we are looking at a transport network, we need to understand the resilience of the transport network so we can see how important our particular section of road or rail or other infrastructure is. So we want to try and avoid and limit failures where possible and reduce vulnerability, and a combination of improve the recovery process so we can quickly return back to service. So we need to make some informed assumptions in our assessments. Go to the next slide. So we have, in our report from research, we have proposed a number of resilience-based design approaches. One was to kind of consider the importance of that particular infrastructure. And on the right-hand side, you can see different levels of importance defined based on the functional needs of that particular infrastructure. And that sets the resilience expectations for what we are going to design. And the next step is to kind of look at what approach to take for the design. And that depends on how important the resilience is. So we define low to high levels of resilience expectation. And depending on that and the importance level, we choose different design approaches consistent with that. So on the next slide, so we need to look at the impacts of the slope failure, and Doug talked about the runout. So this is an example on the right-hand side where, based on the learnings from this research, we looked at the runout from landslides along this coastal highway, and based on that, we were able to come up with recommendations for improving the resilience of the highway, such as improving the alignment. So you can see how the research outcomes could be used. So at a high level, we want to avoid the potential hazard, try and enhance redundancy in the network, and select appropriate forms that reduce the potential for damage and allow faster recovery. From that perspective, kind of more ductile performance like embankments enable quicker recovery compared to more brittle mechanisms and big failures. And then we can focus on strengthening key vulnerabilities. And on the next slide, so the design approach, the resilience-based design approach is looking at increasing complexity of investigation analysis based on the importance of earthworks, choosing pseudostatic equilibrium methods for low consequence earthworks, and then we might look into permanent displacement analysis for moderate performance requirements. And then if we need a higher performance, then we might look at more sophisticated stress deformation or time history analysis for major slopes or severe consequences. And on the next slide, so we provide some recommendations as to how to derive seismic hazard levels based on the importance category of the particular infrastructure. And you can see on the table on the right-hand side, we provide some guidance for use in New Zealand. And then we also need to take into account topographical amplification, which Doug touched on. This is the amplification of shaking due to the presence of steep slopes. And again, depending on the slope angle and the slope height, we provide some recommendations as to how much more amplification we need to allow for. And the third aspect is to allow for incoherence of motions. So the way in which the ground motions affect slopes, not all parts of the slopes are affected equally and at the same time. So we need to take that into account when we design slopes. So from that perspective, we kind of provided recommendations for how much shaking we need to consider in the upper quartile of the slope where most slope failures occur or initiated, as you saw from Doug's presentation. And then if we are looking at larger failures over the full slope, then we use a reduced ground acceleration because the ground acceleration won't be the same over all heights of the slope. And in the next slide, So it's important to look at then the slope performance. So, and we want to avoid large failures which can close the infrastructure for long periods, because remember, quick recovery is quite important. But then we can accept small failures which can be cleared quickly because they don't have a big impact on the functionality. So that enables focus on the large failures and savings in allowing smaller failures. And also ductile behavior of materials like embankments, we can use a displacement-based design to look at how much displacement we can tolerate, and therefore we can recover quickly. But for brittle materials like rocks, we need to be really careful because even small displacements can lead to reduction in strength and therefore loss of functionality. The next slide. So in addition to this, we also need to look at rockfall risk because that poses a safety hazard, and we recommended a number of measures like use of benches and use of rockfall fences and catch pens. And we need to also consider safety during the design using a safety by design process, as well as consider safety during operation and during aftershocks after an event. We go to the next slide. So the key takeaways of this research are on the next slide. A resilience-based design approach is highly valuable for the development of economical and sustainable solutions to focus on functionality and recovery of infrastructure. We need to be careful about brittle failure mechanisms, in particular rock slopes, and we need to consider the fact that they could not accommodate a lot of displacements before failure. A displacement-based design is appropriate for fill slopes, but we need to kind of consider how much displacement is tolerable because before you get too much failure. And we need to look at the mechanisms of landslide runout during an earthquake, as well as what could happen in post-event scenarios where you could have storm events which could mobilize materials disturbed in the earthquake. So a resilience-based design should be assessed and used to design networks, and this will enable us to design more resilient infrastructure. And the next slide. So now we finish this presentation. To consider questions, I will hand over to Sharon, based in our Canadian office. But before that, just note that in a couple of weeks' time, there's the third of our webinar series, which is going to focus on landslide hazard mapping and how that can be used to improve the resilience and response for our infrastructure. Over to you, Sharon.
Thank you, Brava and Doug, for a fantastic presentation. We have just a few minutes for some questions. I will just mention again the housekeeping items quickly. Please continue to log your questions in the question box, and the presentation slides are available to download in the handout box on the control panel. I will start with a question about slopes. How do you use topographical effects in the design of slopes?
Yeah, I think as I was just mentioning briefly, the topographical effects are very important when we are looking at high slopes because the free field motions we get from standards such as the Geotechnical Module 1 in New Zealand or other standards globally just provide what shaking you get in flat ground, which is competent ground. But when you have slopes, you get changes in the shaking levels, which vary across the slope height. So a lot of slopes fail at the top of the slopes because we have weaker material, but also we have amplified shaking. So we need to focus on these mechanisms at the upper part of slopes and use amplified shaking. But if we are looking at potentially larger mechanisms, then we need to consider the incoherence of motions and therefore reduce the ground motions when we consider full slope height failures. Otherwise, we will be looking at too conservative and unrealistic failure mechanisms.
Thank you. Another question is, how much displacement can you tolerate in the design of slopes?
So what do you say, Doug? You have looked at that in a bit of detail in our research, haven't you?
Yeah, well, it depends on the material as well as the the way that it's behaving. So, for example, the greywacke materials, the structurally controlled and tend to be shallow failures. It didn't tolerate much displacement before they collapsed, and so you had complete evacuation. Some of the deeper seated failures tended to tolerate more displacement, but for the size of the earthquake and the duration of that shaking, that displacement continued on, and then they still collapse. So it's not a simple sort of threshold. If you're below that, you're safe, and if you're above that, you're not safe. There's quite a bit of detail, and so you really need a good, I guess, model of the materials and how the failures might develop.
Thank you.
Thank you, Doug.
Do you have any recommendations for using the surface erosion protection systems on the highly weathered rocks?
Doug?
Yep. So for more frequent type, and particularly for storms, then that's a useful way of preventing erosion and progressive development of failures. I guess for earthquakes, the effects of that are going to be quite confined to the shallow surface, and so deeper seated failures aren't going to really see much difference. And it's probably mostly useful for the upper parts of slopes where you've got those weaker materials, and it's important to kind of prevent the runoff and erosion from developing over steepened slopes above the infrastructure.
Yeah, just to add to that, when you have rock slopes, one of the ways you could avoid safety hazards is like by pinning some mesh onto loose areas of rock, so that could help erosion and mobilization of rocks, which could pose a safety hazard. Just to add that this is a brief presentation today, but for people in New Zealand, we are planning to run some day-long seminars early next year, so to provide more insight into designing of slopes for earthquakes and other perils.
Thank you. The next question is about costs. Would the design of earthworks slopes for resilience substantially increase cost, and is that really affordable?
Yeah, good question. Often people automatically think greater resilience or greater cost, but doesn't necessarily need to be. I think I covered this in a bit more detail in the last webinar. So if you would like to go back, can have a look at that. You can get that on YouTube. So you can search for that on YouTube. But in brief, if we take into account resilience and take resilience focus from an early stage of design, we can avoid having to spend a lot more money. And actually, some case studies I've looked at indicate that we could actually make savings in the design. So the important thing there is to take an early focus on resilience and look at how we can improve the location, alignment, and the form of the infrastructure so that we can improve resilience without additional cost.
Thank you. The next question is, has land ownership been an issue in addressing mitigating hazards, for example, geological hazard being outside a highway corridor?
Doug, you might want to share some insights from the Kaikoura experience where you were involved in the recovery of the transport networks.
Yeah, so in Kaikoura, I guess it was helped that a lot of that land along the coast was essentially reserve. So the government was the landowner as well as the infrastructure owner. There obviously was private property nearby. I don't believe there are any issues because of the people that owned the land were having those problems themselves with landsliding, and so they were grateful that there was work going on. And so to answer the question, it wasn't an issue, and generally that didn't affect the remediation or the solutions that were put in. So it didn't mean that work couldn't happen outside the road corridor. But obviously it's a consideration, and it's not just land ownership, but it's also the sensitivities with archaeology and iwi as well, which is an important consideration.
And to add to that, I mean, from our experience in dealing with a lot of large infrastructure projects, that has rarely been an issue. Often when you talk to people, they understand the importance of improving resilience, and they are willing to accommodate that. Because in effect, often it kind of reduces their vulnerability as well, right? Because otherwise their land is vulnerable.
Thank you. A question about sustainability assessment. Is there any sustainability assessment calculation that will be to be considered with respect to design of foundations, retaining walls, and embankments?
Yeah, very good question. It's there's something which we are looking at in detail as part of the New Zealand Geotechnical Society climate change focus group. But in brief, often improving resilience improve sustainability. A lot of projects we have looked at, we have been able to improve resilience without having to spend a lot of money and spend a lot of concrete and steel by taking more of a nature-based solution approach. And that approach not only helps improve resilience, but also improve sustainability and cost. For example, if we had cut slopes, just making the cut slopes a little bit more gentler, even if it involves a little bit more land take and a little bit more earthworks, it's a lot more sustainable and economical than having to cut slopes and then use a lot of shotcrete or anchors or steel to strengthen that slope.
Just add to that a particular example from Kaikoura. There was a bypass done about 20 years ago, and the cut slopes for that were cut very flat, a lot flatter than they needed to be from a stability point of view. And the reason for doing that was so that the land could be returned to the farmer for grazing. So they were shallow enough that the sheep could still walk on it and graze. And those slopes performed perfectly. Basically, there was no damage, deformation, no cracking or anything. And the fill embankments through there, which were actually steeper than the cut slopes, they suffered a lot of cracking and displacement. So, you know, this approach for sustainability is also for the long-term use of the land around it as well.
Thank you. I will take the last question, and any additional question that was asked will be answered directly by the presenters. And this is regarding the Kaikoura rebuild that you mentioned, Doug. What was done in the Kaikoura rebuild to reduce the risk of similar big landslides in future events?
Yeah, so you saw some of those photos, the height of the slopes and the proximity to the corridor. There's not a huge amount to do before you start getting in the way of other hazards. So there was a lot of uplift in the earthquake, and so that was the uplifted sort of shore platform was used to move the road and the railway out away from the hill slopes, you know, where possible. In other areas, new bridges were built to allow debris flows to pass underneath the corridor rather than over the top of it, and then slope stabilization and more sort of localized measures were used where there was no other alternative. So avoidance was the best and option, but it's not practical in all situations.
So if I can add to that, one of the key learnings from the spate of earthquakes and hazard events we have had in New Zealand, the Christchurch contemporary earthquake sequence and Kaikoura earthquake is that, and that early focus on resilience is important. It's important not just for projects, but also when we are looking at recovery from events. So usually we have a little window of opportunity when the events have happened, and then there's a response being carried out before we start to look at recovery and restoration of the infrastructure. That window provides an ideal opportunity to look at resilience and think about what we can do to improve resilience when we are doing the rebuild. And that is particularly relevant to now for us in New Zealand, where we had this spate of storm events and cyclones which devastated the northeastern part of the country. And if we can focus on resilience before we start into rebuilding, then we could improve resilience a lot more than if we do that later.
Thank you, Brava and Doug. Thank you all for joining us today. As Doug mentioned, as Brava mentioned, this is the second webinar out of 3 dedicated to resilience to geohazards. We hope to see you in our upcoming and third session beginning of November. So thank you everyone for joining today. Have a wonderful day, and we will wrap up the session now. Thank you.
Thanks. Thank you.
Thank you very much.